to understand response of IT system to external drivers, which come into the model as upper boundary conditions. These are convection electric fields, which can be defined through several empirical models. This is basically interface between magnetosphere and upper atmosphere, and particle precipitation, which are responsible for auroras and for ionospheric ionization, and precipitation usually picks up during storms and substorms. This model solves Navier-Stokes equations and for a variety of species, neutrals and ions, the dominant species in upper atmosphere. And as an output, we look for plasma neutral density, temperature, velocities for plasma components and for winds. So that kind of gives us a bigger picture of how everything is connected. The way we do run GITM, well, the people usually run GITM, let's put it that way, is that we have input solar wind parameters, solar radiation, we have drivers, and we have outputs. Typical drivers are derived from statistical averages, so they're kind of large scale, a time scale over 15 minutes, and spatial scales about 500 kilometers, which really shows you kind of large scale basic physics. But it's been shown, especially recently, quite a few papers, that energy transport into ionosphere thermosphere depends on temporal and spatial scales, and physical mechanisms can be very different depending on scales. For instance, if we look at smaller scale features, we can account for more energy coming in than if we just look at some average large scale structuring from drivers. One of the indicators of energy dissipation in ionosphere is so-called Joule heating, which is analogous to resistive heating when we have heating due to current passing through conductor. So it's governed by conductivity, electric field, and in case of plasma, also V cross B and this velocity of neutrals. Just a bird's view that this is distribution of Joule heating if you look on top of the Earth, like basically polar regions, from the top, northern polar regions. So this is a pole, and this is the regions where we have, say, release of energy heating throughout certain magnetic storm event. But if we go into more accurate description of what is going on in terms of heating using reconstruction, data assimilation, reconstruction of measurements, we started seeing, well, a little bit more fine structures, and it's not that simple. But if we look very regionally, very local, specifically at radar measurements, which shown here in green, and this is just the components of electric fields through hours, we see this is a lot of peaks which are not captured by data assimilation shown in blue. So we're potentially missing all effects due to this large electric field excursions. And I'd like to highlight this work done in Dane's team when they developed empirical model, tried to infuse this variability at mesoscale and improving Joule heating estimates. Just to show you, these are electric field components. These are time in hours, and red shows the large scale features and observations of black dots. So indeed, a large scale model can miss a lot of observations, so we need to find a way to incorporate them and say this kind of model is an important step in that direction. What we've done in our group, we looked at very regional driving at high latitudes in Alaska region, and we used ISR, which is incoherent scatter radar measurements, to estimate electric field and merged it with large-scale models. So here regionally we look at mesoscales, below 500 kilometers, and time scales less than 15 minutes. What we did, we developed an add-on software framework on top of GITM that doesn't require source modification. And we tested it for specific event March 2nd, 2017. So this is a picture of how this poker flat incoherent scatter radar phaser looks like. It's located at University of Alaska's research range close to Fairbanks, Alaska. And it provides a three-dimensional imaging of electron density features. And lots of this and measurements can also be used to infer lots of ionospheric parameters. As the results been published in JGR. So these are kind of schematic of experiments from which we used observations. So this is phaser, longitude, latitude, and these are beams. So measurements going along the beams, and we also used estimates of electron density along the beams, a temperature, and electric field. A technique was developed by Nichols et al. In 2014 and improved by Semeter, Varney, and their teams. So they estimate electric fields on 2D grid from line of sight velocity measurements. And of course, a bunch of assumptions going into that, but it seems to be a nice step forward to try to measure actual electric fields locally. This is an example of reconstruction of a time snapshot of electric field. And what we've done, this is kind of large-scale picture of a driver for GITM. So this is electric field potential, which ensures link between magnetospheric processes and what's going to go on in ionosphere, thermosphere. At kind of large scale, you don't have many fine features. When we look at region of phaser, here it reduced. It's hard to see at this scale, but you see it's a little wiggle here. So basically, we blend very regional measurements with Weimer model. This is Weimer model, and see if that's going to alter our estimates of plasma parameters and heating very locally. And it did. Here is one of the results, this ion temperature comparison. Here is temperature, Kelvin, and on a horizontal scale, time in hours, 6:30, 6:40, so it's like every 10 minutes. Gray shows measurements, and a range of gray shows error of measurements. Yellow is a result of ion temperature reconstruction from a model using large-scale driving only. Here, red, it shows our approach to introduce this regional mesoscale driving, and we see that we're doing somewhat better. So it gives us confidence to continue. Indeed, if we use a realistic electric field derived from very local measurements, you can show that heating, shown in red, is actually increasing. It could decrease. It depends on the specific event, but it does show there is a difference. We are working in making this source an open source code release, and we're working with Aaron Ridley, who is one of creators of the GITM, together with Yue Dane and Gabarthot, to put it on GITM GitHub depository. So hopefully it can be used by other people and can be used with other models, not necessarily GITM. Another aspect of driving by like mesoscale and small scales processes is we can actually look at ULF waves. These are compared small scale processes, smaller scales at 500 kilometers size of driving, and there have been some work done showing that if we look at how much energy often wave can deposit in ionosphere, thermosphere, when they come in from magnetosphere, that can actually increase, in certain instances, our estimate of heating to maybe by 10%, sometimes even 25%, compared to what we had without waves. And since often waves, ULF waves, are pretty ubiquitous in geomagnetic storms, this is something we like to look into as well. I just would like to move on real quickly to other parts of my presentation. So what I try to do, I just try to introduce our modeling framework, which allows to incorporate incoherent scatter radar measurements into GITM drivers to provide a better estimate of localized heating. However, we need to admit that it's still work in progress, and for instance, electron density modeling is still not perfect, not where we want it to be. And we think one of the reasons that we need to include more realistic particle precipitation, which will change our estimate of electron density. But anyway, first results seem to be encouraging, and I would love to have a longer discussion with Professor Dane's group, or maybe join an effort on this topic. Do you have any questions?
So I think Dr. Deng said she had a question, so I'll invite her to ask her question. But other than that, we don't have any questions in the Q&A, and if the audience wants to chime in, please type in a question and we'll get it answered. So I think Dr. Deng is still muted, but maybe she's not ready to answer her question.
Right.
Ask her question.
Yes. Can you hear me?
Yes.
All right. Very nice work. Yeah. I just wondering, the HIME module.
Yes.
So what's the typical, observational domain? How big is the size, and what's the typical resolution for that high resolution domain?
Okay. Let me go with that. So basically, we look at this region, which is from 64 to like 71. Well, I would say it's like within maybe 10 degrees, 10, 15 degrees latitude, longitude. Electric field temporal resolution estimate is about 1 minute. And spatial resolution, it's you can see here is, well, it's about 10 kilometers. But we really don't really use drivers at this high resolution, so we downsample it. We figure out, we've done some research and figure out if you try to find a sweet spot between requirements, between how much time we need to run it, and basically loads on the computer, and with accuracy we want to achieve, we think that 0.75 degree by 0.75 degree is optimal for us.
All right.
But it is a pretty small region, unfortunately, but it's better than rockets.
Sure. Yeah. Thank you.
Thank you. Okay, then I'm going to move to another part of my presentation. So we talked about driving of upper atmosphere from above, but it's also driven from below. Upper atmosphere starts from a little bit under 100 kilometers in altitude, and a lot of stuff is going on below that. There have been a couple of review papers published recently which look at ionospheric disturbances during earthquakes, tsunamis, volcanic eruptions, and explosions. But in our group, we mostly stick to natural hazards. This schematic kind of briefly shows you the observational instruments which we can use, observables, and retrieved quantity, which help us to understand how surface could be ground surface or ocean surface coupled with through low and middle atmosphere coupled with upper atmosphere. We're particularly interested with radicaltation, GNSS ground-based measurements, and air glow imagers. We'll look at total electron content signature and air glow images signature. but also quite interesting results on in situ observations for Gauchi and Grace. So what's going on if we have earthquake? We have shift in the ground, upshift. Sometimes it's kind of shear motion. Sometimes a combination of that. It causes it generates waves in lower atmosphere, which can propagate horizontally but also vertically, and they propagate up to ionosphere and thermosphere, and then it causes generation of waves and some disturbances in upper atmosphere as well. And you see those disturbances in total electron content changes. They're very subtle changes, but with precise GPS technique, we're able to detect them. And we are mostly interested in cold seismic and cold tsunamic ionospheric disturbances. Also, Xin Meng in my group, she led an effort to develop wave perturbation model to link disturbances on a surface through vertical velocity measurements with input or lower boundary conditions to GITM to be able to drive GITM directly by measurements of ground disturbances. This WP-GITM infrastructure has been published and is still under continuing development. So basically, this WP model is a semi-analytical model which helps propagate waves from the surface to kind of the lower boundary of GITM. This is an example of event simulation, which was a Chile earthquake, which happened on September 2015, and local time was 7 p.m. It was a fairly strong earthquake, and we had several GPS sites in the vicinity, which also measure vertical velocity displacements. And this is an example of such observations from one of the sites. Here is time, horizontal axis, and vertical velocity in vertical axis. So time of the main shock, and then you see changes in vertical velocity. We kind of smoothed these changes and retained only first 20 harmonics, looking at some kind of large scale disturbances, and then we fed them into WP-GITM. We also went further. We decided, okay, usually earthquake disturbances are very asymmetric. So why don't we use measurements from yet another site? And you see the ground velocity reconstruction shows much lower velocity disturbance. So definitely disturbances were stronger to the north than to the south. And these stations are not at epicenter. We also used attenuation factor, understanding that basically, well, amplification factor, sorry, understanding that signal is going to be attenuated in the sides and should be stronger in epicenter. So Xin developed a procedure how to merge these measurements and to drive GITM. And this is an example of TEC perturbations output from a model. And they indeed show very nice north-south asymmetry with much stronger disturbances to the north, which is consistent with observations. Then we've done more detailed analysis. We looked at all these sites, GPS sites, and say, okay, what about time series of TEC data? And this is example for, this is time here, and these are different ground sites from a local GPS network. Previous model, when we used driving only with one ground base station shown in purple, and present model shown in cyan. We see we're still not perfect, but at least it appears that we managed to catch the beginning of the event. We don't quite get phase yet. Magnitude is close for some sites. For some sites, it's still a bit off, but we do see signatures in ionosphere in our model which correspond, which are consistent with observations. So current state of WP-GITM, that we have augmented new features into the coupling model, including effect asymmetric radiative pattern of a seismic source. And we use seismic measurements from more than one location, try to understand how TEC is disturbed. We're currently working on improving of this model. For one thing, our semi-analytical part, WP, assumes isothermic atmosphere, which of course is a pretty rough assumption, but it was something that we just needed to start with. Right now, we try to incorporate stratified atmosphere, which we believe will improve our estimates of electron density and phase of the measurements, and match the phase of the measurements better. Do you have any questions to this part?
I don't think we have any questions quite yet.
Okay. But, if you have any questions, you can always send me email, just ask you Dan, and I will be glad to provide you references or answer your questions. So
actually, I'm sorry, I'm going to interrupt with my own questions so quick.
Sure.
Not to get too far off the rails, but I know that in literature there have been some papers concerning ionospheric disturbances acting as a precursor to earthquakes and other type events. And I know that's pretty there's not a consensus on that whatsoever. Could you comment on that at all?
I think it is a very important topic, and it would be great if we will be able to have reliable precursors so we can warn people and have early warning system. But this topic is controversial, and we try to steer clear from precursors in my group, even though we have to review papers and participate in some of discussions. We mostly deal with co-seismic and post-seismic events. Let's say that we are not convinced, but we keep an open mind, and we do hope that scientific community will resolve this question.
Great, thank you so much.
Okay, now I wanted to have a couple minutes to introduce my group and what we're doing there. Currently, we have about 15 people, and we also have several affiliates. Some of affiliates are close at UCLA, some affiliates are in Florida. So we have people all over the place, and but core of 15 people, including postdocs. We work on ionosphere and atmosphere remote sensing, which includes kind of two major research directions. Remote sensing, advanced processing, data delivery, creation of data sets. We support NASA and also a couple of international missions, for instance, ocean altimeter missions with France, and also doing fundamental research sponsored by NASA. And of course, we do scientific analysis of the data sets and high-end computer modeling. Originally, our group started as support of deep space network because, ionosphere is something that was an impediment for communication with our space missions. God knows what's going on with this ionosphere. Sometimes it's disturbed, sometimes we have problem with signal. And then it became actually quite an interesting topic in itself because, as we know, one person's noise, somebody else's person's data. And then a whole topic of space weather and importance it for Earth infrastructure. So currently our main directions are ionosphere study, data processing and analysis based on GNSS measurements, which doesn't only include GPS. We also work with Galileo and with GLONASS. Development of processing techniques We have our own ways of processing raw, so-called Rhinox data, and bias fixing algorithm. That's mostly Python-based. GIM, global ionospheric mapping, also global atmospheric assimilative technique. We do data assimilation. We're also interested in evaluation of forecasting capabilities of current models, and our branching out of natural hazard studies, diagnostic research, and advanced warning system, kind of natural offshoot of this ionospheric branch. Also, we work with other groups at GPL, try to develop near real-time warning system based on GPS measurements, because we can see TEC changes kind of over the horizon, and that's a possibility to detect tsunami signatures in open oceans by TEC measurements. Atmospheric research. We study UTLS region, which is upper troposphere, lower stratosphere. We produce our own data, including temperature profiles and other parameters. For this region, we're processing a decade of data from different missions, including CHAMP, COSMIC, GRACE, TerraSAREX, COMSAT-5, and a couple others. We also study climate trends and involved in intercomparison between data centers, for instance, in Austrian GRAS, European Data Center, and also with UCAR. We develop our own retrieval techniques specifically tailored for planetary boundary layer research. This is like 2 kilometers of the ground. And our section, which a group is part of, also delivered receivers for COSMIC 2. So we are involved in analysis of temperature retrievals from COSMIC. Also, we're interested in polarimetric radiocultations. It's a totally new thing and very interesting with a Spanish group in Barcelona. We're participating in PAS satellite project. And it happened to be that if you look at properties of polarized signal in radiocultations, you can tell a lot about, for instance, water vapor. And it can help in weather forecast, especially to estimate when rain is coming. We also work on planetary radiocultations naturally. What we do for Earth can be extended to the planets, and remote sensing for Venus and Mars capabilities. We have some ideas about that, and we're working on that, since GPL is a planetary lab. We also have several cross-disciplinary efforts, including planetary seismology. One of my group members is the system engineer on the InSight mission, and he builds a seismometer that is on Mars right now. So we're very proud of that. He was part of the big team of that. So kind of a brief summary. So we're doing ionospheric data delivery and mission support. We deliver data to NASA, NOAA, and Federal Aviation and Air Force, certain specific ionospheric data. We're interested in radiocultations, specifically atmospheric radiocultations, but we've done some ionospheric radiocultations and would like to go back to that. Planetary boundary research, planetary radiocultations. Oh, I haven't mentioned that we had a couple of active experiments on measuring seismicity from balloons. Well, in California, we have lots of earthquakes, luckily not very big ones so far, but you can actually measure infrasound signatures from balloons. And it's a very nice way of monitoring things and has lots of applications for studying seismicity of other planets, because sometimes it's better to have scientific ballooning measurements, remote sensing that actually landing. Also, we worked on scintillation, ionospheric scintillation. It's due to density irregularities in ionosphere, and tsunami early warning system. And we're also quite interested in machine learning right now. So that's kind of a brief summary of what we do. And thank you so much for giving me this opportunity and for your interest.
Thank you so very much. So we do have a couple of questions that have popped into the chat. We have one from Dr. Yuji asking, going back to the part about earthquake and the ionospheric disturbances, will the earthquake affect the GPS device itself, the receiver itself?
Absolutely. Well, usually this GPS device is actually built in a bedrock, but of course the bedrock is shaking. Quite often we have a saturation of a signal. Sometimes the device is damaged. Sometimes it's just a measurement of the kinds that it's really hard to process them. That's why for earthquake we have to use measurements of receivers which are not at the epicenter. Maybe some people can really reduce those measurements, but I think it's pretty difficult if it's possible. So we use measurements off center a little bit.
We have another question from Dr. Deng. She asks, she says GIM, but I'm not sure she means GITM there, is using data assimilative technique to generate the global TEC map, correct?
I'm sorry, I was not clear on that. I mentioned kind of everything together. Yes, we have GIM, which is Global Ionospheric Map, which is totally product, kind of result of fancy interpolation. And also we have GAME. I didn't really talk about GAME at all. This is a separate data assimilation technique, which uses simple physics-based model for persistent and ingested data like TEC measurements, ionospheric radial rotation measurements, for instance, from old Cosmic 1, and it uses common filter. So it's totally separate data product. Totally different software.
Okay, great. And then one last question I see so far is that an anonymous person, but I suspect that this is somebody who is familiar with ionosphere thermosphere dynamics, asks, I remember that ISR can get electron number density and electron velocity from 200 to 600 kilometers by electron scatter. So as you mentioned, in polar regions, it's this electron velocity totally contributed by the E field or also included by other dynamic factors like wind? Since the electron velocity needs to be converted into EX and EY and then potential, thank you. I'm not sure about the last part of that question, but that's what has been typed up.
That is a very good question. And it's totally correct comment. Well, I mean, I agree with it. I'm not going to judge it. I agree with it. The thing is that the technique we use is fairly simple. So we say, okay, this is convective electric field. So it's totally defined from radar measurements, and it's not very well defined problem mathematically. So we use a bunch of assumptions. For instance, we try to pick up field which is the smoothest one. So it's not a kind of single value problem, and indeed, additional parameters, additional factors like neutral winds, which we don't measure in concert, they gonna to affect it. That's a good question. Actually, I'm gonna just think about it further. Thank you for reminding me about it.
Well, at this point, I think we're out of questions from the Q&A. I'm not sure if any of our moderators have anything else, but if not, this is the point where the audience is clapping at their computers with a lot of energy, of course. We've gotten a couple of thank yous and some appreciation in the Q&A. But from all of us on the Colloquium Committee and the Physics Department, thank you so much for spending your afternoon with us. And thank you very much.
Thank you very much. I wish I were there in person, but we'll make it happen sometime in the future.
Excellent. Thank you so much.
Thank you.